Educational Module Statistics for Data Science. Learning Unit Core. Built-in data types and objects. The entities R operates on are technically known as objects. Everything in R is an object. The basic data structure in R is the vector. Vectors may be either atomic vectors or lists, and they have three common properties which include the type of the object, which we can get using function typeof, the length of the object, meaning how many elements it contains, using function length, and additional arbitrary metadata about a object, using function attributes. In the figure you can see the data types supported by R that belong to the more general vector object. Atomic vectors must have their values all of the same data type. There are 5 basic data types supported by R that we'll discuss: logical, integer, double, often called numeric, character, and complex. R also offers a rare type that we will not cover in this course, called raw. The character could be A or my text. A numeric could be 2 or 15.5. An integer could be 2L tells R to store this as an integer. A logical can either be true or false. The complex could be 1 plus 4 complex numbers with real and imaginary parts. R also operates on objects called lists. Lists are ordered sequences of objects which individually can be of any type. Lists are known as recursive rather than atomic structures, since their components can themselves be lists in their own right. Both atomic vectors and lists have one dimension. To have the complete picture of R's base data structures, we should also mention the ones that are used 2 dimensions or even more. The table below lists to the 5 data structures most often used in data analysis, organized by their dimensionality 1D, 2D, or ND, and whether they're homogeneous, meaning that all contents must be of the same type, or heterogeneous, meaning that the contents can be of different types. Apart from the vector object, there is one other related object: null. Null is often used to represent the absence of a vector as opposed to n, which is used to represent the absence of a value in a vector. Null typically behaves like a vector of length 0. Almost all other objects are built upon these foundations. Note that R has no zero-dimensional, thus no scalar data types. Individual numbers or strings, which you might think would be scalars, are actually vectors of length 1. Given an object, the best way to understand what data structures it's composed of is to use strength function. It is short for structure, and it gives a compact, human-readable description of any R data structure. As we already mentioned, atomic vectors of length 1 can be considered as scalar types. There are mainly 6 data types present in R. Basic data types are numeric, character, and logical. In these examples you can see variable my_age taking the numeric value 28, variable my_name being assigned the character value Nicholas, and variable is data scientist taking the logical value true. The character object can be created using either double or single quotes. If the object itself contains quotes, you should escape them using the \character. On the right side code example, we see variable my_name being assigned a character string value that contains a single quote, so we need to escape it using the \. If you want to see what type the variable is, you can use function class. For example, executing class my_age will print numeric to the console. You can also use the functions is.numeric, is.character, and is.logical to check whether a variable is numeric, character, or logical, respectively. For instance, see the last code example on this slide. Typically a vector will have more than one values, as it is defined as a combination of multiple values, numeric, character, or logical, in the same object. A vector is created using the function C for concat_combine, which combines the vectors it will receive as arguments and returns a new vector. Below we construct a numeric, a character, and a logical vector and fill them with values. The combining mechanism is more evident in the second example, where we construct vector y using an existing vector x with 5 values, then value 0, and then again vector x with each value replaced by its opposite. You can refer to elements of a vector using subscripts like in this example where we access the third and the fifth element of vector y. Vectors can be used in arithmetic expressions, in which case calculations are performed element by element. It is not necessary that all vectors participating in the expression have the same length. If they don't, the value of the expression is a vector with the same length as the longest vector in the expression. Shorter vectors are recycled as many times as needed, perhaps fractionally, until they match the length of the longest vector. In the following example we construct two vectors x and y and then a new vector v using the arithmetic expression 2 asterisk x plus y plus 1. Vector v has the length of the longest vector in the expression and is constructed by adding together, element by element, 2 times x, y repeated twice, and 1 repeated 4 times. R has a number of facilities for generating commonly used sequences of numbers. We can create vectors as a sequence of numbers using the colon operator and function CQ. The colon operator will produce the sequence of numbers between the two operands we have placed to its left and right side. For instance 1:5 will give us sequence 1 2 3 4 5, or -2:3 will output the sequence -2 1 0 1 2 3 and 5. The :1 will output sequence 5 4 3 2 1. The colon operator has high priority within an expression, so, for example 3 times 1:6 is the vector C3, 6, 9, 12, 15, 18. The function CQ is a more general facility for generating sequences. The first two arguments specify the beginning and end of the sequence, and if these are the only two arguments given the result is the same as the colon operator. For example CQ37 is equivalent to 3:7. There are also arguments that can determine the step of the size and the length of the sequence. For example CQ-1, 4, 0.5 will create the sequence -1.0, -0.5, 0.0, 0.5, 1.0, 1.5, 2.0, 2.5, 3.0, 3.5, and 4.0. Another useful function for generating sequences is ret, which is used for replicating an object in various ways. For example, assuming that x less than c1 2 3 4, then ret x 3 will create the sequence 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, and 4. It thus repeats the complete vector 3 times from start to end. Ret x each equals 3 will produce 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, and 4. In other words, it repeats each element of x 5 times before moving on to the next. Back to our tennis players example, we can give a name to the elements of a vector using the function names. See the first code example. It is possible that we may have missing values in our datasets. In our missing values or missing information are represented by a not available. Let's say for instance that we want to enrich our data on tennis players by adding another vector with their year of birth and that we do not have this info about Nadal. Crazy, right? Vector players _ birth would be populated like in the example below. Arguments to CQ may also be given in named form. In this case the order of the arguments is not relevant. For instance, CQ2 equals 30, from equals 0, by :5 is equivalent to CQ0 35 and outputs the sequence 0, 5, 10, 15, 20, 25, and 30. Also, CQ from equals 4, 2 equals 10, length equals 6 outputs the sequence 4.0, 5.2, 6.4, 7.6, 8.8, and 10.0. Note that in the second example we could not define also the step of the sequence. We can determine only the absolutely necessary values for creating the sequence, and in case we only provide from and to values then step is assumed to be 1. If we want to check for net values in a vector we can use function is.net. The result of is.net is a logical vector in which The value true specifies that the corresponding vector element is not available. There is a second kind of missing values named NaN, not a number produced in situations where mathematical functions don't work properly. For example, when we try to divide by 0, the function is.NaN is true for both NaN and NaN values. To differentiate, you can use function is.NaN, which is true only for NaN values. Another case of special value used in R is INF, which represents infinity. For example, if we ask R to compute the value of 1 divided by 0, it will output INF. You can have either positive or negative infinity. Matrices, or more generally arrays, are multidimensional generalizations of vectors. In fact, they are vectors that can be indexed by 2 or more indices and will be printed in special ways. Let's start by the matrix type. Matrices are not a separate class of object in R, but vectors with 2 dimensions. They have rows and columns and they store objects of the same mode. Matrices are created with the function matrix or by using the assignment form of function dim. When we use the dim function, we start by defining a vector and then transform it into a matrix with specific number of rows and columns. In the first example, we use function matrix to create a matrix with 5 rows and 4 columns and fill it with numbers from 1 to 20 inserted by columns. In the second example, we start by creating the vector with numbers from 1 to 8 and then we use the dim function to convert it in a matrix with 4 rows and 2 columns. Another way to create the matrix is to bind columns for rows using RB and cbind respectively. When we define parameter byRow equals true, the matrix is filled by rows. byRow equals false indicates that the matrix will be filled by columns, and this is the default mode of filling a matrix in R. In the first example, we can see how to create the matrix using the cbind function to place the 2 vectors as columns in the new matrix. It is also possible to define labels for columns and rows using parameter dim names of the matrix function, which should be assigned a list value as in the following second example. Arguments of the list function are 2 vectors containing the names of rows and columns respectively. Arrays are similar to matrices, but they can be multidimensional, meaning that they have more than 2 dimensions. For example, an array with dimension 2, 3, 4 is made up from 4 rectangular matrices, each with 2 rows and 3 columns. Arrays can store only one data type. An array is created using the array function. It takes vectors as input and uses the values in the dim parameter to create an array. In the example, we create 2 vectors of different length and then we combine them to create a 3-dimensional array that consists of 2 two-dimensional matrices with 3 rows and 3 columns each. As we already discussed, a vector having all elements of the same type is called an atomic vector, but a vector having elements of different type is called list. So, an R list is an object consisting of an ordered collection of objects known as its components. There is no particular need for the components to be of the same mode or type. A list could for instance consist of a numeric vector, a logical value, the matrix, a complex vector, a character array, a function, and so on. Here is a simple example of how to make a list. The list contains a matrix with 3 rows and 2 columns, a vector with characters, and a list which contains an atomic character vector and an atomic numeric vector. We can check if, let's say, ECList is a list with the type of ECList function and find its length using length ECList. Components are always numbered and may always be referred to as such. Thus, if ECList is the name of a list with 4 components, these may be individually referred to using double square brackets. If, further, ECList double square brackets 4 is a vector subscript array, then ECList double square brackets 4 square brackets 1 is its first entry. Another way to access a list element component is by its name, like in the example using the $operator between the name of the list and the name of the list element in quotes. In the previous example, you probably noticed that for accessing a list component by its position we used single square brackets and not double square brackets. Both ways work, but there is a slight difference. Double square brackets gives us the selected component whatever type it is, but single square brackets gives as the selected component as a list. So, single square brackets is more flexible than double, because you can use all the tricks of vector and matrix indices and also use logical vectors and negative indices. With double square brackets you can use only a single value, either a positive number or a component name. Also, two or more lists can be merged into a single list that contains them using either the C function or the append function. In this example we see how to merge lists 1 and 2 into a new list, list 12. We print the merge list to see its contents element by element, along with element names, as both initial lists had named elements. Data frames are two-dimensional, matrix-like data structures, where the columns can be of different types. Think of data frames as data matrices with one row per component but with possibly both numerical and categorical variables. In R, the data frame is a special case of a list, which has equal length components. Components is placed along rows and they must be of equal length equals number of columns. In a sense, the data frame stores components that share the same structure, meaning the same number and type of data. In this example we see how to define a data frame that stores different types of data for each trainee. Trainees are stored in row and their data per type in respective column positions. We create the data frame using the data.frame function, and when we print the data frame object we can see its contents arranged in rows and columns. We can also see the structure of the data frame by calling the strength function like in this example. We can extract specific data from a data frame, specific columns for all rows, specific rows for all columns, or specific range of rows/columns, like in the example presented here. In this example we see how we can extract only the data of the first three objects stored in the data frame. We see how to extract a specific column for all objects, meaning all rows. And we see how we can extract specific columns and specific rows. The data frame can be expanded if we add new columns or new rows. We can add a new column by referencing the name of the data frame and the name of the new column using the character in between, and then add values for the new column to each component, i.e. each row of data. To add one or more rows we can create a new data frame with the additional data and then bind the two data frames on a row basis using the rbn function. In this example we start by adding to our data frame an additional column that contains the country information for each trainee. Then, we create a new data frame that contains the same columns as our initial data frame but has data about new trainees in the form of new rows. After creating the new data frame we print it to make sure it contains all the data. In the second example we bind the two data frames in one. The new expanded data frame contains all data for all trainees. We confirm this by printing the new data frame to see all rows and columns. A factor is a data structure used for fields that takes only predefined, finite number of values, in the form of categorical data. For example, the data field such as marital status may contain only values from single, married, separated, divorced, or widowed. Another example is to define a field flavor to only take on values vanilla, chocolate, or strawberry. The different possible values a factor field can take are called levels. We can create a factor using the function factor. Levels of a factor are either defined, or if not defined, they are inferred from the data. For instance, the statements below create a factor without predefined levels and a factor with predefined levels regardless of whether all levels appear in the factor elements. By default our sorts levels alphabetically, but we can override this when we define levels literary. Factors are stored internally as integers which have categorical labels associated with them. This is clear if we see the structure of a factor variable using the strength function. We can access factor elements in various ways similar to accessing vector elements. In the example we see how we can access the second element of a factor, how we can access the second and the third element, or even all factor elements except the first one. Another option is to use a masking vector of logical values, and this way to only access the factor elements in positions that correspond to true. We can assign new values to vector elements the same way we would do it in a vector. In the example code on the bottom right of the slide, please notice that if we try to assign to a factor element a value that is not among the levels of the factor, we get a warning message and a value is assigned to that element. We can overcome this if we add a new level to the factor and then reassign the value to that element. To add a new level to the factor of the previous example, we can use the levels function and the vector concatenation function C as shown below. This figure shows all data structures we discussed so far, conveying their differences. The only data type missing is the factor, but it is easily distinguishable from the rest. As we can see, the first three data types contain only same type of elements and differ in dimension. We start with one-dimensional vectors, move to two-dimensional matrices and then to three-dimensional arrays. In the second row we have data frames and lists which contain different types of elements. Data frames contain in columns same type of elements, but rows may differ, while lists are even more flexible since they allow any type of data in each position, even lists.